Okay, so we left it there with this new era thing that actually finally worked. Now we've got this problem. So we've got the problem here now that is that this doesn't seem to be comparable. So. The argument, yeah, this doesn't seem, so the argument doesn't seem to be comparable, whatever that means. Whatever that means. Or metrics, but not with symbolic metric expressions as you've used it. Okay. Okay, expects numerical values. You should not subtract the max directly. So here's another approach. Since you're dealing with symbolic computation, there's no numerical overflow risk. Okay, that's now an interesting response, actually. Since we're dealing with symbolic computation, there's no numerical overflow risk with the softmax function, which means you can safely remove max from the symbol. Oh, okay, so that is actually a big statement. So you can safely remove max z from the symbolic softmax definition. So what is the purpose of? I mean, you know, that probably comes down to the fact that I just probably don't, you know, we don't understand it exactly. Exactly why is this implemented this way, right? Here it says because there's no numerical overflow risk with the softmax function. Maybe the question is then, why do you okay, why do you need to check for the overflow in the first place then? So modify the sum part of the softmax definition to correctly compute the sum of the explanation. So maybe, okay, so it just suggests that as a corrected function. I mean, that was definitely a useful answer. I didn't need that. But now the question is, I'm curious about these. I mean, that is so. So in a traditional softmax Python implementation, why are we subtracting the max element? It transforms the row scores and transforms them into a probability distribution. The standard formula for the softmax element is this, where exponential function. We often subtract the maximum element from each logic before applying the exponential function. This modification does not change the output of the softmax function because we're subtracting the same constant from the numerator and the denominator. However, it greatly improves the numerical stability of the computation. Why? It avoids numerical overflow. Okay, yeah, because it's very large. You see, that is interesting, right? That is a good thing. That's why that's one thing that I like a lot, right? So when you're kind of diving into some of these implementations and you're like, why is that piece there? And then you realize it's just patch over patch over patch sometimes. Okay, yeah, that just I think that makes sense. It took us 2 days or 2 sessions to get there, but that's fine. Let's run this now. And now we are getting to the next error, which is so what is the next expression? Is valid only for square numbers. Why isn't it square? Why isn't it square then? Exponentiation is only valid for square matrices, obviously, because you're. Why? I mean, why is that obvious? I guess this is where exactly happening here. Let's debug that element. Why is it that exponentiation is only to a matrix? This line exactly. Not the element y is exponential. The error message indicates that isn't square matrix, which is an issue because 2 results from is a 1 by 3 matrix. To fix that, you need to apply element y. That's true. That's what we want. So we want the for functions for this purpose. I just apply func is the correct version of so. Okay, that is a good thing to know as well. We use these here as well. Apply func, so that should actually work. Yeah, but we're not doing max val, okay? So we're just doing x. So you're probably making the same mistake here. You are making the same mistake. Copy this. Do that like that, and then essentially that's what we do. Okay. I'm not so sure now. Is it divided by the sum? Again, are we dividing element by element? Is it gonna work? So use something to invalid limits given. The debug, this is actually useful, really. Oh, wait a second. Why isn't it breaking with that? Why isn't it breaking with these in the first place? Okay. Summations. So it's breaking at the sum element. Breaking at the sum element. So it's going because it's a great use of sum function SumPy library. To construct a sum using SumPy summation must have limits, start and end values, but it's called with a series of expressions that don't have any summation limits defined. The thing is, before I did that, this was correct, wasn't it? Before we did that? Yes, look at this. That was correct here. So why did you apply func? That's interesting, right? It's interesting. It's like how there's a lot of back and forth needed with some of these things, right? It's like if you're making sort of, whenever you're doing a correction, it just kind of makes the same mistake again when it suggests a solution to one thing, but then it generates a whole function with the same mistake somewhere else. Because this was here correct, I think. Now let's see what happens now. Okay, now we get something else. Invalid limits. Now we get invalid limits again. Z shape. Well, because it's probably is what we have to do, right? Or what? I think it's probably, let me debug that, but I think the problem here is that we're using Z. The elements of EZ, exactly. I think you just change that. That'll be my guess. do it. Okay. Sums over the correct range of indices, and it should sum is the elements, not the symbolic matrix Z. The sum it should be over the columns, which corresponds to summing over the second index since it's a vector in a case. I'm not so sure about copy pasting all of that. What if we just do this? Is this solving the issue? Invalid limits given is still the same. And in whatever it suggested before, do we have the whatever it suggested before, the why is it loading? Sorry, had the mic off. Why is it loading that slowly? Oh, sorry. That's where I wanted to go. Whatever it suggested before. Here apply, then sum. Here it did a I0 output size. Do it for J. Oh, I got row sum matrix wide. Let's see. So essentially, in range. Okay. So that's just forcing it to give it like an actual array or something. Okay. And then do it. Let's see if that works this way. Essentially, integer, simplify, deprecate, simplify, expression with limits. Oh. It takes a lot of back and forth to just get something that if I am going to here and I say I'm searching for symbolic implementation of softmax for a matrix in SymPy, I'm not so sure if it wouldn't actually find it faster. Nah, that's definitely not going to be the one that works. If I open these, so that's an unanswered question. Right? Yeah. So symbols, it makes a symbol here. Oh my god, using SymPy symbols for summation index. Okay, but now I think we got it somewhere else. No. Yes. Okay, that seems to have worked. Okay. Now we are at line 37 already. So we're at the loss function here. Okay, good. That seems to have worked. That's already progress, people. That's already progress. So now we're here, and it's probably going to be a similar problem. So it basically says invalid syntax. Invalid syntax. Debug with EI. The debug with EI is very useful. The problem lies in the user sum with the generated expression. Generated expression. Oh yeah, of course. That again, we're having the problem here, right? So we need to probably give it again limits and whatnot. So it needs to do the same thing here. It needs the limits. Okay. Okay. So now we're gonna define. So you define these symbolically, and we run it. We got it. Beautiful. Beautiful derivative. It's a beautiful derivative. I like it. It's a beautiful derivative. How can we use it now? Okay, we got a derivative. The derivative of loss with respect to W2 is this one. Why doesn't it actually print the message? Why doesn't it print the message? Why this doesn't print this? But it seems like yeah. Okay. That's it, right? I mean, if that's what I'm printing, correct? I guess so. Okay, so we got it. So what we'll do next is try to figure out how to use this. I guess what I'm trying to say is we have this expression, right, for these elements. So for these kind of shapes and whatnot, right? We could also make these variables symbolic. I guess that would be a bit too crazy probably though, but we got this for that. So we've got these very complicated thing, right? I'd love to see if we could simplify these, because essentially what we're saying here is, can you write that like it's all, yeah, the thing is it's all laid out in terms of all the components of the matrices, right? Can so copy, can you take these, can can the AI, so can you take these, the symbolic expression SymPy based below and compacted using matrix symbols, not just the elements, not just the expanded version element wise. You know what I mean? Like because essentially what we want to see is whether we get to that similar thing where I think it was basically saying that can we have the same result starting off with the raw formula and SymPy to calculate the derivative with respect to W2, which was that the derivative was this derivative of L, which was derivative, you know what I mean? Like, yeah, but it's not something. Now let's see what the AI says. I don't know if it has enough. Oh yeah, that's way above the context window for these guys, but maybe. Give me a second, guys. One thing that I need to do is pause this for a second. I'll be back in a second. Okay, so we're back recording. I downgraded to 3.5, so probably that's not gonna work well, but let me see if I can. Can we do this? It's 3.5 smart enough. Hey, but It's too long. I can't. But it was plus. Okay. Oh, not here. So give me a second. I actually need to switch accounts. Give me a second, okay? Okay, so we're back at recording. This is ChatGPT 4. I'm not sure if it has a big enough window. Has a bigger window, but I don't think it's gonna. I don't think it's gonna do it. This is too complicated. Oh, what am I doing? I just copy pasted that. Sorry. Can you? Compress it symbolically in terms of just matrix symbols, not the expanded element-wise version above. Is it able to access that? Can I do this? Can I do this? Certainly. Of course I can do that. Into matrix form using standard linear algebra. I mean, that would be pretty cool if that would do that. What? The compressed form would look like that? Really? So, I'll just, okay, so we'll I'll take a screenshot of these. Why is this ChatGPT GPT-3 for music production? What the fuck? Really? Has it saved? That's pretty cool. Can I share a link to this? Copy link. That's pretty cool. I'll take that. And I will try to analyze this in the next session. See if that is. I'm not so sure it did the correct thing. Like there's two sources of error, right? So on one side, like GPT-4 might be getting these wrong, obviously, this compression. I could also just ask SymPy, so can I take the derivative and use SymPy simplify? Like if I use simplify, I don't think that is gonna. I don't think that is gonna print something nicer though. Let's see. But let's use that. Maybe dust. Maybe it can. I don't know. The thing is, here is at the very element level, right? So I don't think it can read that as matrices. I have the feeling that one of the things that this expression has done is just basically break down the matrices and just give you a formula at the element level, right? Which is not necessarily bad, but let's see. It's running forever anyway. I will give it a minute or two more, okay? But yeah, I mean, that is kind of the. If I could take a look at these, if that's correct, if that somehow matches these, right? Because here what we're doing is what we're doing here. Well, we're saying that the derivative of that 2 is basically the transpose of that times dz2. And dz2 is these. Essentially, that's what we're saying. So I don't think that is correct. I don't think what we got is correct. I mean, that is very simple, right? So this is actually it's very simple. So that's what that's what I was expecting to arrive at. But again, the whole thing is, symbolically speaking, a1 is of course expressed as all this shit here. So maybe it's not that wrong, right? Because a1 is this. And sorry, I switched to that. Not that, you know, not that. This whole x here is a bit weird. There's the tangent. There's that expression in here. W2. I don't know. Maybe not that far off, but that's just taking too much anyway. See you next session.